In March 2011, a magnitude earthquake of 9.0 struck the city of Kesennuma in Japan. This catastrophic event was followed by a tsunami that destroyed the town, and as civil engineers, it's very critical to analyze the event to implement strategies that will minimize future destruction. As a hydraulic engineer, my segment of the project consists of creating a plan that will redirect water and dissipate the energy of the waves to decrease the velocity. In order to maintain Kesennuma's culture and beauty, I've avoided creating channels within the city. Therefore, I've decided to create 2 channels at approximately 1.6 miles away from the city. In addition, I've placed 3 twin-wing barriers and 1 maze-lamp barrier within that vicinity. The purpose of placing barriers within the outer limits of the city is to reduce the energy of impact generated from waves before reaching city limits. The twin barriers will rise into a vertical position, and the maze-lamp barrier will close 5 minutes after a 6.0 earthquake occurs. The barriers will allow water to be redirected into the channels, which one channel starts at the mouth of the bay and ends into a dam. Based on calculations, this strategy will reduce the inflow velocity by 40%.
The geotechnical process began with the analysis and classification of the soil in the city of Kesennuma, Japan. The Japanese only required standard penetration tests. Therefore, only SPT was performed to obtain our soil profile. Our structural engineer was responsible for designing an industrial building and a bridge, and because of soil liquefaction at project sites, our foundation design demanded drilled shaft piles. Here is an Excel worksheet that has different loads applied to piles of various diameters. This table was provided to illustrate different combinations of safety and cost effectiveness based on the diameter of the piles. Extra research was conducted in order to address liquefaction issues and explore alternative solutions for soil improvement, not just for our project boundary, but for the city as a whole.
As a construction engineer, I will attempt to create a proposal for how to rebuild the city of Kesennuma. The most urgent needs of the city of Kesennuma would be the task of clearing the rubble and building temporary housing for tens of thousands of people left homeless. This will be part 1 of my 2-part building endeavor. Part 2 will include more permanent buildings and infrastructure, including roads, bridges, port facilities, and multi-family apartment complexes. The multi-family buildings will be 4 to 6 stories tall and roughly 40,000 square feet per story, with the bottom stories being parking structures. These buildings will be strong enough to act as a safe evacuation center as well as apartment complexes in case of another catastrophe.
Keeping the original street network with minor changes, I separated my project into 5 different neighborhoods. Roads within the neighborhoods were then divided into 4 different categories, which are major and minor arterials and collective residential streets. Then I redesigned every category based on the Highway California manual along with roadways, parkways and intersections. These examples show cross-section of roadway, parkway and intersection of major arterial.
As the structures engineer for Group AfterShock, I decided to use reinforced concrete as the building material for new construction. Reinforced concrete has shown its ability to withstand severe structural damage during earthquakes, resist impact loads, and it's also a relatively inexpensive building material. One of the aspects of the project was to design a bridge spanning across the port and into the mountainous area to the east. This bridge was designed in order to promote tourism, ready the city for economic growth and expansion, and also to serve as an evacuation route. Caltrans bridge design details were used to design an adequate cross-section of the deck. 2 6-foot diameter spiral columns were designed to support the bridge's ultimate distributed load of 33.5 kips per foot. SAP 2000 was used to analyze the bridge under ultimate conditions, and large shear and moment values lead me to believe that 80 KSI or lightweight concrete should be used for more adequate design. A 6-story Japanese-style commercial building will be built within the on-land water line from the previous tsunami, and the bottom 2 floors will serve as a parking structure. The building will support the gravity load with columns, an 18-inch thick slab, and T-beams spaced 15 feet on center. Included in design is a 7-foot by 7-foot column footing used to support the proposed 1-foot by 1-foot columns, and lastly, a 2-foot thick by 8-foot tall reinforced concrete shear wall was designed to follow ACI 318.